My name is Nikola Perković, not Jure Barbalić, and I'm here as a substitute for Jure. Unfortunately, he wasn't able to come here, so yeah, I'll do my best to present this team. And unfortunately, Professor Žarnić isn't here because these two presentations were actually connected. So too bad you aren't able to hear this previous presentation, but it is how it is. So I'll talk a little bit about numerical models. So agenda looks like this. First I'll give a short overview and introduction, then a research solution, methods and result, and in the end we will conclude about numerical models. So what were you supposed to hear before this presentation is about this hybrid timber glass panel. So this is invented, let's say, by Professor Rajčić and Žarnić, and it's high ductility hybrid timber glass panel. It consists of laminated glass element surrounded by CLT frame. As you can have heard before, the CLT element is cross-laminated timber that has better mechanical characteristic than, let's say, usual timber. So dimension you can see here in a picture, and what my colleague was trying to do is to do a numerical model of this panel on a global way and some local corners, and you will see afterwards the friction. So the first problem that we had after we did some experimental tests by seismic loads, that the problem is actually in corner where we have the glue rods. So because of the test that experiments are sometimes take some time and take some money, we decided we try to do some numerical model to save some time and money. So what were the problems? So the problems is actually the complex behavior of this multifunctional and potentially smart hybrid panel, and the key and what we are trying to do is to make a digital twin of the real panel, where interaction of digital with the real can be designed and simulated with high performance computing. Some of the challenges that we face is like I said before, the joint of the hybrid panel. So we try to do a numerical model of joint in panel corner under cyclic lateral load and under some static loads. The second thing we try to model is the friction, because when you see this. When you see this element, it looks like a usual window, but the difference is that this this laminated glass, is actually bearing element. So that's the main difference. And one more thing that make it, let's say, special, it's that it's capable to be earthquake resistant, in the way that this glass panel, can freely slide into the wooden frame, and in that way you can dissipate the energy. You will see that in the next few slides. So the key goal was the optimization of the model side and precision in order to reduce the processing time. What are some solutions? So after we did some seismic tests, we saw that the problem is the corner. So we cut the corner, we cut the joint of the timber frame, and do that in the first place. Did some laboratory test that will be the base for the numerical modeling. So we did experimental test of joints in the corner due to European standard, and the sample size was the same like in real panel, defined by cross section and the depth of the glass. We used 3 different rod diameter 10, 14 and 20, and all with nominal strength of 8.8. After that, after we obtained some data and results, we did some simulation, and they were performed in the ANSYS. that will show you in this slide. So how it goes? We did first some 3D solid model just of the corner with all the materials and characteristics of the real panel. I mean that, but steel rods, adhesive layer, and central and lateral lamella, and of course steel bearing and rails. In these pictures, you can see the detailed numerical model. It looks just like in the test. So, some few basic steps was first we need to make a geometrical model. I made that in Inventor Autodesk. Then the most demanding part was defining a contact actually between the adhesive layer and timber. After that we need to find a proper mesh, because we need to find not too big mesh or not too small elements, because if you put very small elements it will the procedure will take you a lot of time, and if you choose a big elements then it's not really correct. So that was one of the main problems, and afterwards we conclude that the results were actually good. So the basic of ANSYS wasn't enough, so to achieve the calculation precision, both plastic and material hardening, plastic features and material hardening, were introduced into the modeling. Steel rods was inside, the steel values which occur in non-linear area. As I said before, the most demanding part or particular attention was paid to the nature and accurate definitions of contacts. Because you have a few materials, you have wood, you have timber wood, you have glass, you have adhesive layer, you have steel rods, and it's not the easiest thing to accurate define the contacts. And if you, for example, miss friction value between, for example, glass and timber, it will show you bad results. So just to show you quickly how we define the material, mechanical characteristic of materials. So this is the main parts, glass and timber. So before this, we actually measured the characteristics in laboratory. So that was kind of input data for our model. After that, obtained results showed a small variation between test and FM results for the slip models, and the main reason for that is exceeding of embedded strength, which we haven't found yet how to define detail. So we suppose that results differs in that way. As you can see in these pictures, more or less numerical model confirmed the test, and the deformation and stresses are more like in the same area and the same elements. So let's say we are on the good way. Numerical models showed good correlation with read experiments. Even though a part of hysteresis was obtained in a numerical manner, the same should be improved by varying contact zone stiffness and element size, like I said before. We did some seismic test in Ljubljana, and the failure part was this steel rod in the corner, and after some numerical modeling we got the same, and that's a very good thing we succeed. Next model was to define the friction between the CLT elements and glass element, because when the glass element can freely slide into the wooden frame, actually it's the main parameter that due to seismic load, so we have to investigate it a little bit. So this is a 3D model, actually in this picture 2D model with all the parameters and materials, and in these pictures you can see some of the details. So it was two timber elements with glass infill between it, and we put some lateral force, to determine the friction coefficient and the friction force. 3D model for the numerical simulation looks something like this, and in this picture you can see it more detailed. So this steel rod we use to put the lateral force, and when this machine we push the glass to determine the friction stresses on the contact area, and the key goal was to determine the friction coefficient. So this is just comparison to see that the 3D model for the numerical simulation was made very detailed, and we put some LVDT to measure displacement and to measure some stresses. This picture shows just how we put some lateral force. We use springs and then bolts and rods to put the exact lateral force that we have in real panel. After that, these are the steps. So first picture shows the mesh. That's the most convenient mesh that we found. Then we have, in the second picture, we have to define the contact. That shows in next two pictures, this is the contact between the glass and wooden element. This picture down shows actually the input data. This is the real measured displacement that we obtained in the laboratory test, and that was all, the input data for us in the numerical model. And afterwards we got some results, and the behavior, the model goes something like this, where on the left side you can see if it's far away, near, strong, or sliding, and it showed pretty good results. So here, just to show you the comparison between the measured stresses and in the numerical model. As you can see, it's very similar. So let's say the model is confirmed, and that will help us a lot to understand the behavior for some similar elements. So this is the first few steps, and what we are trying to do is to make this model. This is, let's say, local model. We need to do the global model with the real object, and to examine the other characteristics of the panel, like effect of temperature and humidity change, or fire, or so on. And such research would determine the essential characteristic of the panel in terms of structural problems, and enable the introduction of innovative system in building in practice. So generally, this is in this picture you can see let's say the model, the mock-up that we want to build like modulus. So this is the next step. We are trying to model this whole object. To conclude this, what's the key goal? The key goal is to develop this model, and what will give us significant contribution to better understanding of complex behavior. The model is not only connected with hybrid panel, it's also could be applied on a similar joints in any timber construction. Implementation of this model into the model of whole elements significantly simplify the analysis and verification of hybrid panel behavior. So the key goal actually is to find the link between, let's say, real test and numerical model that will save us time and money. We all love science. We all also love time and money. Due to complexity and high cost of real-scale panel test, design and verification of whole panel model is of great importance, and this numerical research is not only directed to scientific public, it's also the precondition for introduction of this type of bearing element into software for statics. So that's all from me. I hope you got something, and hope it was good to you. Thank you very much.